Oh, okay. All right, I suppose I should start. I was just checking the football results. Okay. First of all, any questions left over from yesterday? Yes.
I have a question about this normalization of the MSF. You have actually for the standard model we have low delta B delta L operator, but in MSF we have this operator. So when we do one loop normalization, did we introduce this?
Okay. So the question was about whether those delta B and delta L violating operators get regenerated at one loop. It's a great question, and it's something I didn't talk about yet. That there's a special property of the superpotential that the superpotential does not get renormalized. So you don't, because of holomorphy and various other arguments, the superpotential, you don't generate new operators on superpotential if you don't write them down at tree level. So those operators in particular, the ones you're worried about, won't be generated. Okay, let's crack on then. So now we get to do some phenomenology after you survive the march through index land. So we got all the way to the end yesterday. We decided that we can sort of use supersymmetry as it's one of many BSM models that happen to have within it this parity, and we're going to take supersymmetry as our textbook example, but the following analysis that I'm going to go through could be done for any new model you had, whether it be an extra dimensional model or a little Higgs model or something else that had within it some type of parity. That means that the lightest parity odd particle is stable. Then what we're about to do is the same exercise you would carry out in any of those models. But in supersymmetry, there's decades worth of accumulated knowledge that I can try to distill into the next hour. Okay. So we wrote down that long list of fields in the standard model, and then I claim that once we have this parity, that we can try to find which of those parity-odd fields has all the right characteristics to be dark matter. And from the first couple of lectures, we know the type of properties we want dark matter to have. First of all, we don't want it to carry a charge, which rules out most of the states on that list. So it only leaves a half a dozen or so possible fields within the standard model that potentially could be the dark matter. So let's go through them one by one and see whether they're good or not, and if they are good, what phenomenology they have. So the first one on the list is the neutrino, or the neutrinos, I suppose. So these are the scalar partners of the neutrino in the lepton doublet. Okay, they're parity odd because they're superpartners. They're neutral because they're superpartners of neutrinos, and so that's the two characteristics we need to be dark matter. But unfortunately, they don't work. Right? And the reason they don't work is because they sit in an SU2 doublet, which means they couple to the Z boson, right? And if they couple to the Z boson, they couple to everything that the Z boson couples to, and they would already have been seen. So they were a great candidate until we turned on experiments and did searches for dark matter, in particular direct detection experiments, and I'll get to the details of direct detection experiments in about half an hour, but you'll just have to believe me for now that these are these don't work as is. There are things you can do. Model builders like myself, or not myself, but model builders are very creative. I may not be so creative, but I can't speak for everybody. So there are always tweaks and things you can do to make any state that you think is dead survive as a dark matter candidate. And in particular for neutrinos, what you have to do is you have to try to get some splitting into the game and to remove this neutrino Z coupling. You have to do something to remove this, and what you could do is try to split states such that this coupling is no longer diagonal to the lightest one of these states, but instead, say, couples the lightest one to a heavier one, and then that changes the kinematics of any recoil experiment. But if you don't do this, if you just have the out of the box neutrinos from the MSSM, they don't work because a neutrino can come along and hit a nucleus through exchange of the Z, right? And you can calculate what this cross-section would be, and it's rather large. It's larger than the constraints. Yes?
If this is a property that's just generic of S neutrinos, and we not observe them. Does this not mean that this is going to be a problem with any type of SUSY type thing? It's not just a dark matter problem. This is a problem where the SUSY, like, is this?
No, not at all. No. So the difference for the dark matter case is we believe we live in a big cloud of dark matter. So they are wandering by all the time, and if they have a large scattering cross-section, we would have noticed. Now, if this is not the dark matter, then there's no abundance around us, right? Because it's unstable, and so there's no reason for any neutrino to be around except in an experiment. You could maybe make it at the LHC, but then you'd have to wheel your dark matter detector right up next to the LHC and hope to, see it that way before it decays almost instantaneously in the detector. So it's not possible. So we're taking advantage here. Direct detection experiments, which I haven't talked about, but I will, I promise, are taking advantage of the fact that there is a stream of dark matter passing through us all the time. Okay? Yes. Let's get back to that when I talk more about direct detection. But what it would do is, if this splitting is large enough, right, the problem is that we live in a bath of dark matter, but it's not moving very fast. And so it's coming in with a certain amount of kinetic energy, and if the state it has to get into is just too heavy, even if it converts all of its kinetic energy, it doesn't have enough energy to do it, then this coupling is there, but the kinematics forbid the process taking place. Okay, so that was the first one, it's neutrinos. Yep.
Is it going to be possible to make them massive enough that there's just not that many of them? So like there would be the abundance in order to satisfy the measured density locally.
Good.
Would be really low.
Yes, certainly you could do that. Yeah. Then I don't think you'd be very interested in weak scale SUSY. You're talking about hundreds of TeV. Okay. And again, I'm kind of doing this in a backwards order because I wanted to make connection to SUSY, but we'll get to direct detection within this hour, and a lot more of these issues will come transparent once I draw some plots for you. Okay, so that was case one, no good. Case two, so what are the other neutral states that are lying around in the MSSM? Well, if you remember, I introduced these two Higgs doublets, right? They have neutral components within them. Their fermionic partners are odd. Those are the Higgsinos. There's also within the W, right? There's a fermionic partner of the SU2 gauge bosons, and one of those SU2 gauge bosons is neutral. So that again could be a dark matter candidate. And similarly, the hypercharged gauge boson, its superpartner, which is fermionic, is also neutral. So there are these four candidates that are all neutral. They're fermionic in nature, and they're collectively called neutralinos, right? And they have they have certain combinations of them have the right properties to be a thermal relic and to avoid existing constraints. And this is what we'll spend most of our time within this discussion on the MSSM candidates for the WIMP. We'll spend most of our time on these. The last one is the Gravitino, which I haven't talked about at all, right? And that is the superpartner of the graviton. It's a spin 3/2 object, so it's a fermion, but because it's a partner, it's odd under this parity, and that will be the third candidate, and we'll spend 5 minutes talking about it. But it was once described to me as anybody who wants Gravitino dark matter must have had a very unpleasant childhood, because it only interacts essentially gravitationally. So you can have a thermal story, you can make a thermal story work, and all the dark matter can be a Gravitino. So you can have your toy, you've got dark matter out of SUSY, but you can't play with it, because you can never detect it, because it only couples to us gravitationally. So direct detection experiments, indirect detection experiments won't have anything else, won't have anything to measure. And we'll spend 5 minutes talking. But this is now the list. So this one didn't work. This one is what I'll spend several blackboards talking about, and this will be one I'll spend half a blackboard talking about. Those are the list. Yes?
I have two quick questions. One is, I understand that you can make the mass asymmetry, so one can be more massive than the other. But it's a little odd that you can have a massless particle have a massive partner.
Oh, that's because we've broken supersymmetry. You're talking about why it's neutrinos?
Zero for the graviton.
Oh, sorry, for the graviton.
The graviton is massless. To have a massive superpartner seems a little bit odd.
Well, you should have asked the same question over here, right? Neutrinos aren't massless, but they're pretty close to it. They're very, very light. And
if they have mass, I'm comfortable with you making the other have more mass.
Okay.
I'm not comfortable with going from zero mass, because that's a definitive number.
I see. The reason the masses are different, right, is because we've broken supersymmetry. So the toy examples I did earlier had no SUSY breaking in them, and you saw they had an exactly degenerate scalar and fermion. And then I don't have time to talk about SUSY breaking, but essentially what that does is keeps the properties of the bosons and fermions the same, but lifts the mass of the superpartner. So the superpartner mass becomes heavier. And same over here, right? These superpartners, the Higgsinos can be at the TeV, the WINO can be TeV, hundreds of GeV, but we know the masses of the Higgs, now we know the mass of the Higgs, and we know the mass of the W and the Z, but their superpartners are heavier.
That leads to my other question, which is, I'm assuming that S neutrinos have to be lighter than the neutralinos, that's generally the lightest particle in your system.
Right, so I'm assuming that
How do you prevent the neutralinos from decaying into S neutrinos?
they will. If this is indeed the lightest particle, everything in the darks, everything that's odd in the MSSM will decay down to the lightest one eventually. But under each of these candidates, what I'm imagining is now some combination of these is the lightest parity odd. In this case, I was assuming this was the lightest parity odd, and so then all the other heavy parity odd guys will decay down ultimately to the lightest one. Okay, so. The neutralinos, let's see, so they're collectively called, as I said, they're collectively called neutralinos. I can write down what their masses are. So I have to write down a big mass term now because there's 4 of these objects. And they all mix together in principle. And this neutralino mass matrix, as I said, it's 4 by 4. So you should be recognizing this term from before. This was the mu term that I wrote down. Some zeros in here. Oh my goodness, I'm never going to get it right. Cos beta sine weak angle times mz. See, I've already run out of room. Let's do it over here. What is this? Sine beta sine weak angle cos beta cos. Right, and then this is transported over here and transposed in the right way to make it symmetric. Okay? So these are supersymmetry breaking masses, right? These are the Majorana masses for, in this case, I've written this in this basis where I've done Bino, WINO, let me see, I did H down first and H up. Okay? And that's what the mass matrix is. And in principle, you would diagonalize that mass matrix, find the smallest eigenvalue, and that would be the lightest neutralino. And then there would be 3 heavier neutralinos, and that's the system. But the lightest one is the dark matter candidate. And then, depending on how you diagonalize that matrix, exactly the relative size of all these coefficients, this neutralino may look more Higgsino-like, or more WINO-like, or more Bino-like, but it has mu is the mu term. Remember, I wrote down a term in the superpotential yesterday? That was, in terms of superfields now, this was some piece of the MSSM superpotential. Right, and that was this new term that didn't have an analog in the standard model, and now you see exactly what it does, right? It gives a mass to the fermionic partners of the Higgs bosons. And so, if this term happened to be a lot smaller than these terms, then the lightest neutralino state would be mostly Higgsino-like. If it was a lot bigger, it would be mostly Bino-like or mostly WINO-like. Okay. Sorry? You're asking me why I have negative mu. It's a convention. You can change the signs. There are some relative signs which are convention independent, you know, that they're physical. But I can flip the sign of mu. Yes? Is beta related to the ratio of the vectors? Oh, I didn't tell you what beta was. Thank you. Yes, exactly that. Thank you. So tangent beta, because now this is a 2 Higgs doublet model, right, embedded within the MSSM. So there's now 2 VEBs rather than 1 VEB, and the only thing we know about these 2 VEBs is that they sum in quadrature to the standard model vev, where I've been deliberately vague about whether it's 246 or 174. But the ratio is now a physical parameter, and that's what the tangent beta that appears in that. Thank you. Great question.
Paddy, I don't know if you want to mess with the gauge masses as well.
Yes. So that's what these are, right? I did say these are the SUSY breaking masses that basically, forgetting all this mixing, this would be the reason, or this one in particular, would be the reason why the partner of the W boson has a different mass from the W boson itself, why the Winos are heavier. Because there's some source of SUSY breaking, as there has to be since we haven't seen a supersymmetric spectrum, that lifts all the superneurotic states, and there's a mass parameter associated with each of the gauge bosons, and that is that mass parameter. Does that make sense? And that's why it's on the diagonal, right? Because essentially by itself, it just gives a mass to the Wino. Yes?
Do we have any SUSY breaking mass for the Higgses?
For the Higgses, yes. You can have a B mu term, which is a mixing term between the two Higgses, but not for the Higksinos. For the Higksinos, it's coming purely from the mu. Okay. Now, the W has both a neutral part and a charge part, and similarly for the superpartners, there's a neutral part and a charged part. And so associated with this neutralino matrix, or these neutralino states, are some other states called charginos, right? And they're basically made out of all the charge fermionic partners that I can have. And so I already said that there are some W ones, and there's also a charged fermionic Higgs partner, right? And then there's the charge conjugate versions of them as well. And because these are embedded in the same multiplets as their neutral friends, they get masses from the same parameters essentially. Okay, so you can't talk about neutralinos without also talking about charginos, because their masses are associated with one another. So you can just, in the same way, you can write down a mass term for the charginos. What have I got here? M plus minus. And now this plus minus mass matrix with this M looking like this. So it has an M2. It has something depending upon the ratio of the VEVs times the W mass, the standard model mass, and then it has something else depending upon the ratio of the VEVs, and mu. Okay.
So you wrote down a single chargino corresponding to the Higgs. There were two Higgs doublets, so shouldn't there be a 3x3 mass matrix?
Well, they all package up together to give you one charge plus and one charge minus. So I've just written down the charge negative states here, and there'll be charge positive partners. And that's why this is a 4x4 matrix, but you really would just want to think of it as 2x2, right? Because you can only get a mass term between a plus charge and a minus charge.
So I guess a single Higgs doublet does not on its own give a charge. One is the combination that gives the charge.
Well, remember, 3 of the things are eaten, right? So you've got 2 Higgs doublets, but one of them, or some combination, it has to be like the standard model. You still have to give mass to the charge W's and to the neutral combination. And so what you've done by introducing an extra Higgs doublet is you've introduced an extra 4 states. And there are some of them are charged and some of them are neutral. In particular, 2 of them are neutral. There's a CP even and a CP odd neutral. And then there's one charge state, which means 2 degrees of freedom because it's a charge state. That make sense? And
I guess so, but it's still a little weird. The Higgs doublet, you get.
so let's
So put it this way: the Higgs doublet, you get 4 degrees of freedom.
Yes.
The complex part on top, you make that the charge one, then the axial and the regular scalar. But then in the neutralino part, you have 2 separate neutralinos. They're still complex spinners, right? I'm sorry, that's actually a complex, but they're
vial spinners.
Vial spinners.
Yeah, I know what you meant.
And what about the Higgsino there then? Are there 2 vial spinners, or is there one.
Very good, very good. That's what you said is equivalent. That's the same thing. Two Weil spinners make one Dirac spinner, and you should think of you. Yes. So in sort of Weil spinner language, if you, I've written them as Weil spinners here, and so any mass term would have to look like Higgsino plus Higgsino minus. Otherwise, I couldn't write it down with some mass term. But you can also, in the language you're used to thinking about, you could just call this one Dirac spinner, right? Like that.
I guess also above there, since it's the same mu for that, that's basically like a Dirac term sort of, except for the fact.
Exactly. Well, and that's what a Dirac term looks like in Weil space. It's off diagonal because it has to couple spinner 1 to spinner 2. That's right. That's what somebody already asked me to. Those are the Majorana mass terms that lift the superpartners, right? For the Bino and the Wino. So those are a result of supersymmetry breaking. This is a result of electroweak symmetry breaking, and this is a result of just a term in the superpotential. And you've got all three effects mixing up together. So life is complicated, but. And then you see the same parameter appearing down here, right? You see this is the same M2, and this is the same mu, and then these are also coming from electroweak symmetry breaking. And so you can see that whatever the neutralino mass is, or the neutralino masses rather, you'll have a prediction for the chargino masses. And they won't be that far away because they involve the same parameters, just in slightly different combinations. And that's why you have to write them all down and figure them all out at the same time, because they'll be mixed up in the physics together. Yes?
Is this independent of the SUSY breakings?
This is, yes, I haven't told you the relationship between M1 and M2, for instance. In a given SUSY breaking scheme, there may be a connection between those masses. They may actually be coming from the same physics in the UV, and the only reason they differ is because of RG evolution as you come down. But here I'm being very effective field theory, bottom up, and I'm just saying these are some parameters that were given to me by a smart BSM theorist who had a cool model, right? But this works for all smart BSM theorists, so that's why I did it. Yes? Radiative corrections to what? Thank you. I was about to get to that. Yes, that's exactly right. Let me get to it in 5 minutes. If I don't, ask the question again. But he was asking about the difference between the charge and the neutral. So in addition to this tree level difference, which is usually large, there will be a radiative correction, which is often small, but there are certain limits one can go into, which I'm about to discuss, where the splitting is 0 at tree level, and then you have to worry about the loop splitting. But usually the charginos, because the off-diagonal terms are slightly different and the masses are not exactly, it's only in a certain limit, say for instance, where this is way, way bigger than any other scale, then you can get into a limit where charginos and neutralinos are nearly degenerate, and you have to worry about loop effects. Say again?
So do you mean that the decoupling?
Well, yes, I do, but let me get to that just about now. So in general, I'm saying you have to diagonalize this, and that's hard, so I'm not going to do it here in front of you. But it's illuminating to, when you have a four-dimensional space, it's illuminating to look along the axes, first of all, to see what that space looks like. But the general point, the general place you'll go is somewhere in the bulk where your neutrino is some admixture of all four states, right? But let's just go through the pure limits first, because it is illuminating. Okay, so the first pure limit is to say that the neutralino, the lightest neutralino, is basically the Bino. So some parameters are chosen. Maybe you take M2 and mu, very, 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 very large, and the only light state around is M1, right? You take that limit, and then the lightest neutralino will be mostly pointing in the Bino direction. Okay, and one can ask, if that's the case, what type of interactions does a Bino have? Right, so a Bino is the superpartner of the hypercharged gauge boson, which means it couples to hypercharge. And the states in the MSSM with the largest hypercharge are the right-handed sleptons, right? So remember what I said about the flip 2 rule, right? About you take a coupling in the standard model and flip 2 of the lines to the superpartners. So here is a diagram which will be the process which can help set the relic abundance of the Bino. So here's a Bino, and here is an electron, and here is the selectron, right, and another Bino. So this would be a diagram, T-channel exchange of a selectron, or any lepton for that matter. This is the process which sets the relic abundance, okay? Because these are the guys with the largest hypercharge. They have hypercharge 1. So if you want to have an annihilation, and this is really the only annihilation process you have, right? If you want to have the Beano annihilating into standard model particles in the early universe, you need to have other MSSM particles around so that they can exchange them. And these things have to be light, or relatively light, okay? Yes? Yeah, let's assume they're nearly degenerate with one another. Of course, everything I'm saying, you have to go and look in the details of a model. But parametrically, you know that this is the largest coupling. And so parametrically, this will be the largest process. Now, of course, if the leptons are at 500 TeV and the left-handed squarks are at 100 GeV, that's already ruled out, but let's imagine it was, then that would be the process that dominates. But the parametrics are, it wants to couple to the guy with the largest hypercharge. Okay, and the upshot of this, so you can work out what the scattering or the annihilation cross-section is, and it's just what I said. It goes as some fourth power of the hypercharge, right? And it depends upon the fourth power of this selectron mass, and then the rest of the units are made up by the Beano mass. And it turns out, for reasons we'll discuss, that there is a temperature suppression to this process, right? And so if you want this to have the right cross-section, we talked about the right cross-section, you have to get to the relic abundance a while ago, then you find that the Beano, a pure Beano, has to be less than about 100 GeV, and you need light leptons. Okay, and this puts you into a lot of tension with LEP measurements and other things. So the pure Beano is not a great story, and typically if you came at this from the other direction and said, what would I imagine, what's the bands on these lepton masses, so let me stick the leptons at a few hundred GeV, you'd find that the cross-section's too small, and so the Beano is typically overproduced. Overproduced, right? By which I mean that there's too much of it. So that's bad. Okay, so that's pure limit number 1. Now let's do pure limit number 2. The Beano doesn't work.
The Beano just doesn't work.
It doesn't work. It doesn't. I mean, you can always make things squeeze them, but it doesn't really work. It doesn't want. Let's say it this way. It doesn't want to work. Yes.
Just ask a really dumb question about this mass matrix there. There's obviously mixing between B and W to get this needed photon. Why is there no corresponding mixing with the superpartner mass?
Well, there is mixing between states. You have electroweak symmetry breaking here. That's mixing all of your states.
Those are between the Higgsino, the Beano, and the Wino. But what about if
Right, but if you had mixing between the Beano and the Higgsino, and you have a mixing between the Higgsino and the Wino, then you'll have mixing between the Beano and the Wino.
so there's this indirect.
Yeah.
There's no direct BW or the B tilde W tilde term.
There's no, you're worried about a 1-2 entry.
Yeah.
Yeah, you can't get a 1-2 entry. That's right. Yeah.
About the annihilation diagram.
Yes.
I'm not sure how much to read it because either if you run top to bottom, then you get the same number of.
I am a left to right person.
But then aren't you violating the charge because you created 2 electrons?
There is a, this is plus and this is minus. I'm a left to right person, but I'm very imprecise about the arrows I put on the lines. Okay, where are we going? Oh, Higgsino's, right. So what type of processes can Higgsino's have? So now you take another limit, right? You take M1 and M2 very, very large, and you keep mu light, and then the neutrino will be mostly Higgsino. And what type of processes can the Higgsino have to annihilate? Well, they tend to annihilate into gauge bosons because they have large couplings to gauge bosons. So you can have annihilations into W plus, W minus. So Higgsino through the exchange of charged Higgsinos, right? You can have similar processes through Higgses. into W's. Or you can even annihilate into Z's if you change this to the neutral guy. So maybe I'll write it this way. Okay, so it's annihilation into gauge bosons. The thing to notice is, this gets back to the question that was asked 5 minutes ago, is that if you take the limit where you make the Higgsino the lightest neutralino, so that is to say you take M2 very, very large, and you keep mu small, then you also end up with the chargino that's mostly Higgsino, and whose mass is set by mu. So in this scenario, you often have degenerate charginos, right? Because they're both being set by mu, and that's the only parameter in town. And then you have to be very careful when you calculate this Rayleigh abundance, because the way we calculated it in lecture 2 or something was we basically assumed there was one dark matter state and a bunch of standard model states, and they had, this dark matter state had couplings to the standard model states, and we did the Boltzmann equation and so on and so forth. But now there are other states that are very, very nearby in mass. I can no longer think of this soup as just being one dark matter state by itself plus standard model. It's now a collection of states in the dark sector that have couplings amongst themselves, also coupling to the standard model. And then you have to worry about something called co-annihilation, which we'll go through in detail, hopefully today. Right? And so the dynamics inside the Boltzmann equation get more complicated.
Do you expect in general the charginos to start decaying later on then?
Yes, and that's part of what you have to take into account in co-annihilation, right? That you have an extra state that's around that may, and this second state may have larger couplings to the standard model than the actual dark matter state, but it will ultimately decay into the dark matter state, so it will contribute at the end of the day to the total dark matter abundance. So you need to take its dynamics into account. Okay, and so what is the splitting between this, supposedly, if it was just at tree level and I took the limit M2 goes to infinity, then I would have a charged state of mass mu, and I have a neutral state of mass mu, okay, or two neutral states of mass mu. And then your question comes up, right? That's true at tree level, but we know that one of them's charged, and we know the neutral pions and the charged pions are not degenerate in mass, and they're not degenerate because of electromagnetic corrections to the charge one, right? And so there's a there's an equivalent loop diagram you can draw that correct the chargino mass, but has no effect on the neutralino mass, and you end up with a splitting, a one-loop correction that looks like. I can write it in a nice simple way. You can do the calculation, but you end up with a piece alpha 2 mw sine squared theta over 2. And this number here is, if you work it out, about 166 MeV. Okay? So it depends upon the hypercharge of the multiplet that has the splitting inside it, and on the charge of the charge state. So this is almost always 1 for theories you like to think about, and then for the Higgsino, the hypercharge is a half, so you can put it in and you find that you get a chargino-neutralino mass splitting of about 350 MeV. So that's pretty nearby, right, in mass. And the figure of merit to have to worry about co-annihilation is the temperature. And remember, at freeze-out, we said the temperature over the mass was about a 20th. So if we're talking about 200 GeV or something for mass of the dark matter, that's, 10 GeV equivalent temperature. And so then this mass splitting looks relatively small on those scales. So that means that the chargino states will be well thermally populated, okay, at that temperature. And that's why you need to keep them around when you do the calculation. So people have done this calculation. We'll go through some of the details in a short while. And roughly speaking, actually maybe this is ignoring the, I don't remember now. 1 over mu squared is the annihilation cross-section parametrically. And you find that for Higgsino to be dark matter, then you have a Higgsino at about a TeV. Okay? And if you go heavier, you'd have too much. And if you go lighter, you'd have too little. Make sense? Okay, I want to leave those two there because I want to combine all three limits in just a minute. So limit 3 is the only one left, right? It's take the Wino. Neutrino 0 is the Wino. So then actually you have processes very much like the Higgsino process. It mainly wants to decay into gauge bosons through processes like this, where you just take all the Higgsino lines and turn them into Wino lines. And again, you have a radiative mass splitting, right? Because now you have this triplet, this electroweak triplet that is almost degenerate at tree level. I want to take, what is it? I want to take M2 small and mu and M1 large. And so you see that the neutralino is M2 and the chargino is also M2. And so they're almost degenerate again, and then the loop correction comes back. The difference is, for the Wino carries no hypercharge, right? It's a pure SU2 triplet. It's not, it's the partner of the W, so it has to be in the adjoint representation, which means it carries no hypercharge, and that means the splitting is just this number. So the Wino splitting is a little bit smaller than the Higgsino splitting. Co-annihilation is even more important. So chargino, neutralino, what do I want to call it? Splitting. 166 MeV. And there, to get this to be dark matter, it works for about 3 TeV. The annihilation cross-section parametrically looks similar to the Higgsino, but there's some numbers of order 1 which are larger, just because it carries more SU2 charge, if you like, than the Higgsino. Okay? Yes? You're asking if this formula is correct. Is that what you're asking? Coming from which scale are you talking about? From the. So we want a correction that distinguishes between a state having charge and a state having no charge. And I think the dominant correction for that is coming from the photon. And in fact, there's a small contribution coming from the Z, as you can see, because it's not purely proportional to charge. So it's coming from the U1 contribution. So this is what it is. And in fact, I think this splitting would be true whether it was a fermion or a scalar. This is sort of fairly generic for splitting within a multiplet.
Just a quick question. Isn't the Wino, that pure Wino, ruled out already by Hess?
Good, yeah. So, yeah, I don't know if I'm going to have time to explain Sommerfeld enhancement and all those things, but indeed, you can worry that there are experiments doing indirect detection, which are looking for annihilation, present-day annihilation of dark matter. Again, I'm delaying all this stuff. I'll get to it eventually, I promise. That puts this into some tension. Okay? So, but you can now see what's going on here, right? That this pure story doesn't always work perfectly. The Bino. So remember, at the back of our minds, we want all these superparticles to be around a TeV, and we want them to be a thermal WIMP. The Bino doesn't work because it's overproduced. These ones, this one's sort of okay, that one's not very okay. To get it to work, it has to be 3 TeV. But if I was to combine them in the right way, this one's overproduced and these ones are underproduced. So if I go to a region where I have just the right amount of Bino-Wino mixing, or just the right amount of Bino-Higgsino mixing, then I can probably arrange to acquire the relevant properties, right? I require a little bit of the Bino's annihilation cross-section and a little bit of the Higgsino's annihilation cross-section. And that's the so-called well-tempered story. So the pure story doesn't quite work. I mean, it works in principle, but then now we have data, unfortunately. And I'm joking. That puts the pure states into a little bit of under a little bit of pressure. But what you basically want to do is you want to live on some narrow boundary between Bino-Wino and Bino-Higgsino mixing, right? And then, of course, when you do this, you have to do careful calculations taking into account co-annihilation and all that type of stuff. And I should have had a reference for this, but you can find a very nice paper by Nima and Giudice, I think, and maybe Antonio Delgado. I don't have the number, unfortunately, but if you can't find it, it has the word well tempering in the title. So, okay. Now, what were that? I promised you like 5 things, and you made me go out of order on my notes. Let's see. Oh, Gravitino. Okay, so that's the story of Neutrino, and we'll do the co-annihilation calculation in just a second. But this is, oh, okay, so any questions first? Yes?
So all this is dependent on it being an SSM, like 2 Higgs doublet model, like the mass matrices and everything are different when you have different types of 2 Higgs doublet models, so all of this analysis would be different.
Good question. So in particular, for supersymmetry, needs 2 Higgses, right? And the rules of supersymmetry basically put you into a particular type of 2 Higgs doublet, push you into type 2, which has not that much to say about this. The difference between the different 2 Higgs doublet models are more in the Yukawa sector, which isn't really entering in here because everything here is just in the gauge sector. It's just all the gauginos all mixed up together. This story does get altered, for instance, if you go to something called the NMSSM, which is not the minimal, but the next to minimal supersymmetric standard model. And that's where the less minimal part is you add a singlet. Okay, a pure singlet. And it couples like this in the superpotential, and maybe S cubed, and there might be S terms as well, and you write down terms like that. And then you would have an extra fermion that comes into the neutralino matrix, not into the chargino, because it's pure singlet. So now this becomes 5 by 5. And rather than 4 by 4, and things get more complicated, and you have to do more calculations to work out the relic abundance. Yeah, I thought I was going to say something else based on your question, but now I don't know what it was. Okay, is that okay?
Yeah, that's fine.
And remember, this is just an example of what one would do in any model, right? It's just that we know the story here, so it's easier to explain. Yes. Did I explain why you have to speak up?
Why there's a vector of T over M there?
I did not explain why there's a T over M there. Thank you. I knew there's lots of things I was neglecting. Okay. So this is a general feature of, so dark matter in SUSY is Majorana in nature, right? It's a Majorana fermion. You can see that from just going to the pure Bino limit. The mass term we're talking about is Bino times Bino. Not Bino times some other state, which would be a Dirac mass, but Bino times Bino, so it's a Majorana mass. And so, just in general, if you have a Majorana fermion decaying into annihilating into standard model states, right? You can ask what is the velocity dependence of the velocity of the dark matter? How does this cross-section depend on the velocity of the dark matter? And if it's decaying into light standard model states like I drew here, light standard model states have definite helicity. Okay, so I can ask what happens in this annihilation process. This is a Majorana fermion, so this side of the equation or reaction or whatever you want to call it has to be odd, right? So you need this to be odd under parity. So this side minus 1 to the L, where L is the relative angular momentum of the 2 incoming states times the parity of the spin combination has to be odd. Okay, this is a weird mathematics. I'm going to write it this way. Minus 1 to the L times spin equals odd. The relative velocity, we've already said that T over M is of order of 20th, so the relative velocities we're talking about are like 0.1, 0.2 of C. Okay, so we would like to try and find a reaction that's independent of velocity, because we don't want to pay the price of 0.1 squared, that would suppress things. So we like to think about so-called S-wave processes, which is the case where L equals 0. Okay, and then that means the spin has to be odd, which means spin 0, right, in particular the odd combination. So this whole thing, this side, we would like to have J equals 0, okay? So now you can just think of this as a scalar decaying rather than a 2 fermions annihilating, because that's what scalar decaying is. Now I have the 2 standard model states coming out. right? And one, it's really, I should have written it this way, standard model bar, right? So one is a left-handed fermion if it's light, and one is a right-handed fermion if it's light, right? They have definite helicity. So that means I always get my spin arrows backwards. So that means this is this way, and because this is a right-handed, it's aligned with its momentum. And now you add these up, and you don't get j equals 0 anymore. You get j equals 1. And so you now have an inconsistency. And the way around this is to either insert a mass in here, which is a cost of a small fermion mass, or to not do the L equals 0 process in here, but to do the L equals 1, which is the cost of a velocity. And what I did here is I said I really don't like the electron mass. It's too damn small. I'm willing to pay the cost of the v. And v squared is t over m, so that's why the t over m appears here. So this is a so-called velocity-suppressed process. It is a p wave process, not an s wave process. Thank you for reminding me. I was supposed to go through all that. Yes? Yep?
So you mentioned the Majorana mass that you can start thinking here. The Wino is part of a SU temperature, but how do you give it a Majorana mass without violating gauge variance?
Well, you've broken SU2, right? So it's now, you just want to think about,
So that Majorana mass, is that part of spontaneous symmetry?
that's just for the neutral component, right? So the only thing you want to be thinking about is electromagnetic charge, which is the one thing that's left unbroken. So that's an allowed mass from.
Okay. So are you just leaving the origin of it sort of unspecified?
That's coming from SUSY breaking. So I'm not, remember I was going to rely on cleverer BSM people to tell me that. You had a question. I got it right. Did I get it wrong?
Yeah, no.
Okay. All right. I've never given a talk in the afternoon, so I've totally blanked about when I'm supposed to stop. Is it 1/4 the hour? Okay, good. All right, so the final thing we didn't talk about as a dark matter candidate is the Gravitino. And remember, I didn't want to talk about it because I had a pleasant childhood, so, but maybe we should talk about it just for completeness. So this is a very, very quick, simple story. Supersymmetry is a fermionic symmetry. Okay, it's spontaneously broken because we don't see any superpartners degenerate with the standard model fields. You're spontaneously breaking a fermionic symmetry, so you should get a Goldstone fermion rather than a Goldstone boson. Okay, just by analogy with spontaneously breaking symmetries in the standard model. So there is something called the Goldstino, which is a fermion associated with SUSY breaking, right? But we also know that SUSY is a space-time symmetry. I showed you the fact that two space-time translations turned into two SUSY operations of two SUSY generators turned into a space-time translation. And we also know that gravity exists, and it's a space-time symmetry, and it's a local space-time symmetry. So if you ultimately want to embed SUSY properly into the theory of everything, then you have to make SUSY a local symmetry, right? And then you're spontaneously breaking a local symmetry, and so you know that the Goldstino gets eaten, right? And what it gets eaten by is the fermionic partner of the graviton, right? So because I've made SUSY into a local space-time symmetry now, so there is a graviton that gets a partner called the Gravitino, and that eats the Goldstino that's coming from the SUSY breaking. So then you end up with a spin 3/2 massive fermion, okay? Without the SUSY breaking, there would have been this spin 3/2 massless partner of the graviton, and now it eats the Goldstino and becomes massive. Okay? And it's neutral, so it's a dark matter candidate, potentially. Questions? No? And then the only question becomes, is the Gravitino heavier or lighter than all the other superpartners? And that depends on the details of your SUSY breaking mechanism. In some models, it's very much lighter than the Neutrino, and that's unfortunate. And in some models, it's heavier, and then the Neutrino story can still be the dark matter story. And so, that's how do I want to say this? That's where the Gravitino comes from. So let's imagine now that it was the lightest state. We're in one of the SUSY breaking mechanisms where the Gravitino is the lightest parity odd particle. How do we calculate its relic abundance and things like that? So there's two ways the Gravitino can be made. It also has very, very small couplings, right? It's associated with gravity, So you might naively think that all of its couplings are Planck suppressed. It turns out they're not quite that small. They're really all the couplings of the Gravitino. And unfortunately, I'm about to use a notation that I have not explained, but where this is connected with the amount of supersymmetry breaking. But we don't need to, this is very, very small. So there's two ways a Gravitino can be made. It can either be made by a neutralino being made in the early universe, and then the couplings of the neutralino to the Gravitino are very, very small, and so the neutralino lives for a long time, but ultimately decays into the Gravitino. So it can be made through right. So LSP is the lightest supersymmetric particle, or the thing I've been calling the LPOP, right? The NLSP is obviously the next to lightest supersymmetric particle in our love of TLAs. So in particular, if this is a neutralino, and this is the Gravitino, right? This could take a long time. This could be a slow process. And if the neutralino had the correct relic abundance, maybe you're at a point in parameter space where the neutralino got the right abundance, it was just the right mixture of Bino and Wino, and everything looked great for a while, and then ultimately you find that it actually decays into an even lighter state, then depending on the ratios of masses and things, maybe this state acquires the right abundance from this one. But you also have to be worried that this decay happens so late, it might destroy BBN, so you have to worry about. So that's one way you could make the Gravitino.
Sorry, how would that describe BBN?
Oh, sorry, when this thing decays to this thing, there's a bunch of energy. If the masses are hierarchical in some way, then there's a bunch of energy that's lost in the process, and it goes out into the bath and destroys all those heavy elements that we made with BBN. So all those heavy elements we made in lecture 1 are destroyed, but we know they're supposed to be there. So in particular, you have to worry about the lithium abundance and things like that. The other way it can be made is just through interactions with the bath, right? And you can ask yourself, what is the scattering cross-section? And it turns out it goes, as I said, it goes roughly as 1 over the Planck scale. So this is a very small cross-section, okay? And you can go to your Boltzmann equation and ask yourself, what would I predict for the abundance of the Gravitino? So it's being made. It's being made by two standard model particles crashing together and making a Gravitino. Okay, and the standard model particles are in equilibrium, and the number density is happening early in the universe, so they're relativistic. So their number density is t cubed. So the total number density of the initial state is t to the 6. Okay, this makes sense. And there's no backwards process because the abundance of Gravitinos is so tiny. Their equilibrium abundance is tiny, and I can forget about it. So the first approximation, this process is only happening in one direction. Okay? And so then you can calculate what you get for n3 halves, right? And you find that n3 halves goes as t to the 4 over m Planck. That's right, m Planck. I was worried I got my powers wrong, but that's correct. And we know that this can't be too large, right? So this puts a limit on the initial temperature of the universe after inflation. So this is in particular called the reheat temperature. That's something Jim talked about, right? So this is all going to happen at very, very high temperatures. Standard model particles are going to crash together and make pairs of Gravitinos, and this rate grows very, very quickly with temperature. So not overclosing the universe with Gravitinos puts a bound on the reheat temperature. And this is an example, if you like, of the freeze-in scenario, which you may have heard of, right? Oh, I can't spell freeze. Freeze-in, in the sense that the Gravitino is never really in thermal equilibrium. It's just slowly, over time, being populated. It's starting at 0, and it's getting more and more abundant as time goes on, because the interactions are so tiny that it starts with 0 thermal abundance and gets slowly populated. So you have to, if you want, I don't want the Gravitino to be dark matter because then I'll have nothing to talk about in the next lecture. So, but I just showed you that for full disclosure. Yes, go ahead.
There's no real, I mean, I know you're talking about WIMPS, which is supposed to be says they're weakly interacting, but there's no real evidence for or against weakly interacting versus just interacting geography, right? Dark matter
No,
or-
no. Except Dan will tell you about some potential evidence in his lectures, and I'll mention it briefly at the end of mine. But there are hints of things that are funny, but there's no. We've only, as I said earlier, we've only seen dark matter gravitationally so far, for sure, for real, for sure.
Weakly interacting dark matter, whether or not
It's a prejudice.
it's just because we really want to be able to do stuff with it.
That's right. That's right.
Yes. So in that case, you only get it if you spontaneously break supersymmetry, right?
The Gravitino?
Yeah.
Yes.
Can you still have some breaking terms?
Yes, you can. Yeah. Okay. So these days, if you actually want to calculate how your model, how well your model does for predicting a thermal WIMP, you go to the effort of downloading micromegas or maggraph or something like that, and spending an afternoon putting your model into that piece of software, and then another day or two working out how to run it, and it will calculate for you all the annihilation processes you can imagine, and will solve the Boltzmann equation for you, and work out what your leftover relic abundance is thermally. And so we're going to outline the calculation that's going on under the hood of those clever pieces of software, right? But to do it for real, you have to calculate many, many annihilation cross-sections, so it's often easier to get a computer to do it for you. But it's good to understand what the computer's doing. Okay, and so we already said that in some of these limits, you can often end up with Chargino states very close by to in mass to the Neutrino states. And in addition to those Chargino states, of course, there's a whole sector I didn't even talk about, right? The sfermions, so the squarks and the leptons. Those are also expected to be, in the same ballpark mass as the neutralinos. And it's perfectly conceivable that one of those states could be nearby in mass to the neutralino. It wouldn't be the lightest one, but it could be, say, 5 GeV heavier or something. And in particular, if it was a squark or something, they have very, very different interactions with the standard model than the neutralino, and that can cause all sorts of changes to the calculation for the relic abundance. So far we've been talking about this type of reaction, right, where the lightest one. So now I'm going to just label all dark sector states as chi, and the lightest one will be chi 1, and then there'll be a whole tower of additional states, and there may be processes like this, where they can annihilate amongst themselves to the standard model, or maybe chi2 can annihilate with itself as well, or chi2, as somebody mentioned, can decay. There's all these types of reactions. And if chi2, if the thermal population of chi2 or chi3 or chi4 or whatever is comparable or close to chi1, you shouldn't be ignoring these processes, right? So what one does is you write down a bunch of cross-sections. And now I'm just going to label anything that's not in the dark sector, oh, this is really bad, as X. And I will try to make my X different from my chi. I wanted to sum over X here. So I want to sum up, so basically I'm adding up all possible ways I can get out of the dark sector, right? And there's some index for where I started. This could be the sum over Y now of chi I X. So that's this, I didn't even write down this type of reaction, but this is now a dark sector times colliding with a standard model and turning into a different dark sector and the standard model. And I think I need a Y here. And then there's the decay process. And I want the width for any one of these to decay down to any other and some part of the standard model. Okay? So now there's these types of processes going on at the same time as the chi1 process we've been talking about so much. And you need to take all of them into account. And so then you can write down a giant Boltzmann equation for every state in your theory. And what do you get? Let's see. Ni, Nj, and this is just an analogy with what we had for the single state before. So that's the annihilating two dark sector pieces, and then there's a sum over J not equal to I of some huge mass. So let me write it down and then show you that I didn't need to bother. And I and X, where this is the standard model abundance. Now I want minus sigma x j I and j. So this is just the backward reaction, right? Remember, it's always the difference between two reactions, the forward and the backward. And x equilibrium. And then finally the decay term. N I minus N I equilibrium minus the reverse reaction. Is this legible? I hope it is, because I don't want to have to write it again. Right, so now I have a Boltzmann equation for every single one of my species in the dark sector, and I have to worry about it annihilating against its friends in the dark sector, or it getting populated by decay from some heavier state, or and if I'm looking at that heavier state, how it gets depleted. And then there's also reactions off the standard model that I have to worry about. Once I take all this into account, I'll be able to solve for the abundance of each of these states in the dark sector. Okay? But as somebody pointed out, any state other than chi1 will ultimately decay into chi1, right? Because they're all odd under parity, so they have to, and the heavier guys have to decay down. So the final abundance of dark matter is really set by the sum over all of them, right? So I can call that just n, and that's ultimately the thing I care about. So if there was some way I could massage this big equation to just make this the variable of merit, then I would be happy. Okay? So what I can do is I can, in fact, just sum the whole equation over I, right? When I do that, these ni's will turn into this n. And over here, you notice that these two terms are symmetric under flipping I and j. So if I sum over I, these go away. And that's just what you would expect, right? If I'm summing over all of them, yes? No, I think x means everything in the standard model, because it's sort of implicitly summed, yeah. But if yes, indeed, if I was making x be just electrons and then muons, I would have to sum them. That's right. I'm treating the standard model as one bath, if you like. Okay, so I can do this sum, and it will simplify. It gets rid of these terms. And then I still have a sum over I here. So let me do that. So this turns into n dot. This turns into n. Right? And then I have a sum over I here. And these terms I can now forget about. Thank goodness. And then I make the additional observation that the standard model number density is way, way bigger than the dark matter number density. Right? Because there's a lot more states, and they're a lot lighter. And the standard model is in thermal equilibrium. And so the ratio of any individual dark sector state to the total dark sector state will be approximately given by the equilibrium case. Okay, because of these types of reactions, where are they? These types of reactions here, right? Because this number density is so large, these do a very good job of keeping the dark sector states in equilibrium through their interactions just singly with the standard model. And so then the ratio of any individual state to the total will be roughly the same as the equilibrium ratio. And then that allows me to finally write this ungodly expression, let's write it over here, as now an expression for the total dark matter abundance, taking into account all the dark matter that comes from decays, from heavier things, and so on, as just some effective cross-section times the velocity times the, so now it looks just like the formula we wrote before, right? It looks like a single species Boltzmann equation with an equilibrium number density and a number, and the only difference is what is this effective cross-section. And this effective cross-section is essentially just a weighting of all the different cross-sections that can show up, a thermally weighted thing. Is this too low for people to see? Should I write it higher up, or is everybody? It's very low. Okay, good. So this was high enough, right? Okay, so then let's write it here. Because this is where all the magic is. So you basically have to sum over all the processes you can have weighted in the right way, and the way you weight them is by the equilibrium. Thankfully on this side all you have are equilibrium number densities. And equilibrium number densities are easy things to work out, right? Because you just have to tell me the mass and the temperature and I know what the equilibrium number density is. So you basically take all the individual processes that could take you from the dark sector to the standard model, and you ask the states that are involved in it, how abundant are they? And now you see what's happening, right? If you happen to have a cross-section, so let's imagine we just thought we had the chi-1 cross-section, and chi-1 was a neutralino of some type, so it had weak scale interactions, right? And so we know roughly what this cross-section is. But maybe there was a squark that was 10 GeV heavier. Now a squark has QCD interactions, which are orders of magnitude larger than weak scale interactions. So this cross-section here gets a lot bigger, but it's 10 GeV heavier, so its number density is a little bit smaller, right? Because the temperature is around 10 GeV or something. So now this is, an exponential of order e to the minus a few for the squark state that could be involved in the interaction. But you get to take advantage of the fact that the cross-section is way bigger. So if you have states that are nearby in mass, that aren't too far away in mass, and especially if they have way bigger cross-sections, then they can have a huge effect upon the ultimate abundance of dark matter. And what you need to solve is you need to solve this single species Boltzmann equation, but with this overall weighted effective cross-section. And that's what these computer programs will do for you. So for instance, I think I just said the example I want to write down, but if you imagine a state with a neutralino is chi-1 and chi-2 is a squark, then you have three processes you could imagine writing down, right? You can have, so as I said, chi-1 is a neutralino, chi-2 is a squark, right? So then chi-2 interactions will be alpha strong over alpha bigger than chi-2, chi-1 interactions. And chi-2, chi-1 interactions will be alpha strong over alpha bigger than chi-1, chi-1 interactions. So chi-2, chi-2 is alpha strong over alpha squared bigger than this one, right? And then you can calculate the effective cross-section that we care about, and you find that it is indeed 1 plus alpha strong over alpha times W, 1 plus W squared. And W is this ratio of equilibrium number densities. E to the minus delta X. X is the usual thing, right? X is this, the freeze-out temperature, and delta is the relative mass splitting. So M2 minus M1 divided by M1. And so you can see that if W is appreciably bigger than, it's already got an enhancement because of the coupling of alpha strong over alpha. And if if the mass splitting is large, obviously this exponential wins, but if the mass splitting isn't too large, and typically we're talking about 10, 20%, if the mass splitting is less than, say, 10%, then this co-annihilation process can be important. And there you see it for this particular example. But of course, in reality, there's usually a lot more than two processes. Does that make sense? And this is one of the famous 3 examples of that were written down for the reasons why you shouldn't have trusted the original calculation I showed you for freeze-out, is because there can be 3 very interesting situations where you can't trust that calculation. This being one of them. If there happens to be more than one state nearby in mass, right, then the co-annihilation process is a big correction. Right, the sigmas are different from what I showed you in lecture 1. The other correction is the so-called forbidden channel situation. Right? And this is the situation where, imagine the process is chi1 goes to xy, let's say, AB, so I don't have to confuse you with x's, where AB are in the standard model. And it may be that you look at this process and say, well, the mass of A plus B is bigger than the mass of chi1, so I don't have to worry about this process. But you have to remember that in the early universe, these things are kicking around with a non-trivial velocity, right? They have a certain temperature. And if the difference is small enough, then this process may not happen at 0 temperature, but it may happen a little bit at the temperatures you have, and you have to worry about how much of the Boltzmann tail of the distribution of chi1 is hot enough to allow this process to go through. So, and especially if this process has a large cross-section, then this forbidden channel, even though it's Boltzmann suppressed, can have a large effect on the number density. So that's the other correction to the story I told you on day 1. And the final one is a resonance story that, again, one has to be careful if you have situations where the mass of the dark matter is close to the mass of some other state in the theory, and then there can be a large enhancement in the scattering, in the annihilation cross-section, just through a resonant enhancement. So you have to be careful you take that into account. And these happen in the standard, in the MSSM, right? There are instances, oh dear. There are instances where the CP odd scalar in the MSSM has a mass just by accident close to twice the mass of the neutralino. And then you can have a large enhancement in the annihilation cross-section, and you have to be very careful how you calculate the Rayleigh abundance. Oh, wow, great. I'm almost on time. Questions? Yes?
When you talk about like, there will be Chardino also equals to Neutrino and the label function goes to Chardino, so you talk about the mass is about 140.
Sorry, so the nearby Chardino is a classic example of a co-annihilation channel I have to worry about. You're worried about the decay of the Chardino into the neutralino? Is that what you're worried about? Yeah, and that was taken into account in this term in principle, right? So I included that in the equation, but then I told you there was some clever massaging I could do where since I don't actually care about what the abundance of the Chardino is in detail, I care about the ultimate final abundance of the lightest neutralino. And so I get to sum over a bunch of these processes because they're forward and backwards cancel. Right? Okay, so I think we have one more lecture, and I've told you about SUSY and WIMPS, and I've only ever been talking about one process, which is the annihilation process to get the correct Rayleigh abundance. But there are lots of other interesting processes dark matter can have. And so tomorrow we'll talk about direct detection and how that occurs in SUSY, and we'll also talk about indirect detection, which is very intimately related to the Rayleigh abundance, so it will be very quick. And if I have time, I will try to tell you about dark matter collecting in the center of the Earth or the center of the Sun, usually the center of the Sun, which can happen in WIMP stories, and it leads to an interesting signal. So we can go get coffee unless anybody has any more questions.
I'm not sure if you were why something over I kills those two terms?
We can go through that if you like, but I claim it does. Let's see. So I had j not equal to I here, and then I think I think it will. We'll have to go through it, but I'm almost positive it does.
I'm also not sure why you have the cross-center. So you've got sigma v on the first term and just sigma on the second.
Oh, that was me getting lazy again. Sorry. Yeah, there should be a v in there. Sorry. I wonder when I got lazy. Was it at the blackboard or in my notes? Let's see. Well, it looks like I did it in my notes too. Okay. There's a VJI here. Good. Yeah, it's average too. Thank you. Yeah. I should have. Yeah. More mistakes you'd like to point out in public about what I've done. No, you're all too shy now.
So when we calculated the total n, we went from sigma RG, VRG to sigma effective times 1. That we just had the velocity.
That's right. It's up here. Yeah, it's up here. So you'd have to. There's an IJ on here. But since they're equilibria, yeah, you do have to worry. You still have to worry. That's right. I got sloppy. But you probably can't see it from when you're sitting over there. You're like, the angle is almost flat, right? So the massive parallax on what I'm writing. Yeah, so there's an IJ on the velocity as well. You have to take into account the relative velocities. Oh, since you're still letting me talk, maybe I should have put the reference up here because, as you saw, there's a nice paper that explains how to do these calculations. You can relate them to Bessel functions and things because they involve exponentials. And anyway, there's a nice story there that makes the calculations more tractable that's well described in this paper. Okay, that's how you actually do these the integrals over n effective and stuff. But these days you ask micro omegas to do it. Okay, let's go get coffee and I can answer any of the questions up here.